This clean, highly efficient flame is generated by the most energy-efficient residential oil burner that is currently available. This is the Airtronic burner from Babington Electro Oil of Sweden. It was introduced to the European market 3 years ago. This smoke-like fog is generated by a family of medical nebulizers that has been commercially available in the United States for a number of years. These very diversified products have a common distinctive feature. They utilize the exclusive and patented Babington atomization principle, a revolutionary concept in the spraying of liquids. Soon, a counterpart of the Airtronic burner will be introduced to the U.S. market by an American company. In addition, one of the world's leading manufacturers of appliances will be producing a new line of diesel-fired appliances for boats and recreational vehicles. The purpose of this presentation is to acquaint the viewer with the features of this new atomization concept and the burners that have been developed around it. The main emphasis will be on home heating, but a short summary of diesel-fired appliances for boats and recreational vehicles will also be given. First, let us examine how the Babington principle works. A thin film of liquid passes over the outside of a corrosion-resistant stainless steel atomizing tip and is best illustrated by this glass sphere demonstration model, using water as the liquid. A stream of water is first deposited on top of the sphere so it can spread out and cover the entire exterior surface of the sphere with a thin film. The interior of the glass sphere is filled with compressed air to a pressure of only 15 psig. The air escapes through a small orifice in its contoured surface, and in so doing ruptures the thin film of liquid flowing over the outside of the sphere. The result? A uniform spray with a particle size diameter that is 10 times smaller than that produced by conventional nozzles. The excess water returns to a reservoir and is recirculated. Notice that liquid never passes through the orifice, just clean, filtered air, making the Babington principle insensitive to contamination, even when the fuel contains water and dirt. This high magnification sequence, taken at 5,000 frames per second, clearly illustrates this feature. Here, a dirt particle large enough to clog most nozzles passes over the exterior surface of the Babington atomizer with no adverse effect on the sprayed liquid. In conventional high-pressure burners, liquid is forced through a small opening by means of hydraulic pressure. Nozzles of this type produce a non-uniform spray and are highly susceptible to clogging, especially at low firing rates. Compare the spray from a conventional high-pressure swirl nozzle on the left with the Babington atomizer on the right. Coarse spray particles from the standard nozzle are seen in the upper portion. Note that first a tulip-shaped sheet of liquid is created, followed by a distinct ligament phase, before breaking into various size droplets. The Babington plume of the same magnification shows no ligament phase and much smaller uniform droplets, formed directly from the thin film of liquid flowing over the exterior surface. This fundamental difference in atomization leads to improved vaporization of the liquid particles, better fuel-air mixing, and overall, a more efficient combustion process. With the aid of high-speed photography, we can capture the liquid film rupturing process. In this instance, the liquid film is flowing from left to right to completely cover the atomizing surface and its orifice, but before atomizing air is introduced. Once the compressed air is turned on, it escapes through the small orifice in the Babington atomizer. This causes an immediate rupture of the liquid film and a simultaneous dispersal of fine liquid particles with a mass median diameter of less than 10 microns. In applications where somewhat smaller liquid particles are desired, down to 5 microns, the basic spray can be passed through a conical shroud. When ultrafine particles are required, A spherical impactor is placed in front of the discharge orifice. This provides a second stage of liquid particle breakup, as the basic spray is forcefully impelled against the impactor. The smoke-like fog that is generated by this technique is comprised of particles with a mass median diameter of less than 2 microns. When fuel oil is atomized in this manner, it will ignite and burn like a gas with a blue flame. There is no lower limit on the heat capacity that can be achieved when using an impactor. This makes it ideally suited to many low-fired burner applications, even when the heat output is below 500 BTUs per hour. If we consider that combustion efficiency is directly related to liquid particle size, and the liquid contained in a droplet is proportional to the cube of its diameter, we can make some interesting observations. For example, the ultrafine particles produced with an impactor contain 500 times less fuel than the particles produced by the basic airtronic burner. However, the fuel particles in the airtronic burner contain 1,000 times less liquid than droplets produced by a high-pressure nozzle. By using the Babington atomization principle and its many variations, it is possible to select any desired particle size to suit the particular burner application. The flame can also be shaped to accommodate the heat exchanger design. For example, in the airtronic burner, dual atomizers are employed, a unique innovation in residential heating. The two sprays converge in a flame tube to create an aerodynamic flame holder and excellent combustion stability. A particle size of 8 microns was selected to prevent the agglomeration of particles as the sprays collide, and also to provide good fuel-air mixing. Some air ventilates the atomizing chamber, where it commingles with the fuel spray as it leaves the atomizing tips. Additional air is passed through the center of the atomizing chamber, where it intersects the spray from the dual atomizers. 4 louvers create a swirling combustion process within the flame tube in the vicinity where the dual sprays intersect. This swirling action is stopped by staged blasts of air, which cause the fire to fill the entire flame tube. This highly efficient fuel-air mixing process produces near stoichiometric combustion without smoke. Ignition is achieved with a compact, low-energy solid-state ignition system, so small in size and weight that it can be easily located inside the fan housing. The airtronic burner is powered by a small 70-watt motor. This double-shafted motor drives a power pack consisting of a blower wheel to provide combustion air, a simple compressor to supply the atomizing air, and a self-priming pump to deliver fuel to the atomizers. This power pack is modular in design, and any component may be easily replaced, or the entire unit may be removed by loosening just 2 nuts. Service to the rest of the burner is equally simple. The front flange assembly is fastened to the main housing by means of 3 screws which can be removed to gain access to the atomizing chamber. The unique atomizing chamber with its plug-in igniter was designed for easy removal and installation without tools. Now that we've described how the airtronic burner works, it is appropriate to reflect on the evolution of its design and to enumerate its operating features. The first prototype of the airtronic burner was actually designed to satisfy an energy-efficient need, as identified by the Brookhaven National Laboratory in 1977. According to published reports by Brookhaven, virtually any 1,500 square foot home in the United States can be heated with less than 80,000 BTUs per hour, even if the house is poorly insulated and located in Minneapolis, where the outside design temperature is 12 degrees below zero. Consequently, Brookhaven began a search for a suitable low-capacity oil burner with a variable firing rate from 0.2 to 0.6 of a gallon per hour. It is interesting to note that respected heating experts in Europe supported the Brookhaven conclusion that a low-capacity residential oil burner should be developed. The heating capacity of the current airtronic burner can be infinitely varied between 0.2 and 0.6 of a gallon per hour, with a simple screw adjustment. There are no nozzles or other parts to change. Since the firing rate can be varied, the capacity of the burner can be set to match the exact heating load of the home. This eliminates the losses associated with repeated and unnecessary on-off cycling. In fact, it is possible to literally dial in the stack temperature to extract the maximum possible efficiency from the heat exchanger in which the burner is installed. The Airtronic burner also has a built-in shutter to prevent stack losses through the chimney when the burner is not operating. Even at its lowest firing rate of 0.2 of a gallon per hour, a condition conventional burners cannot approach, the Airtronic burner will cleanly and efficiently burn high viscosity oil, even at very low temperatures. For example, the U.S. Army recently operated the Airtronic burner at 53 degrees below zero, using a winter-grade diesel fuel. These tests were conducted following a 24-hour cold soak of the burner at the same low temperature. It is well known that the combustion efficiency of a high-pressure burner will vary from heat exchanger to heat exchanger. This is because the entire combustion process actually takes place in a chamber that is external to the burner. In essence, the high-pressure burner is a spraying apparatus, or a fuel-air delivery device, whose performance depends upon the physical size, shape, temperature, and the gas dynamics within the firebox of a furnace or boiler. By contrast, the Airtronic burner was designed with a built-in combustion chamber where virtually all combustion takes place. This makes it totally insensitive to the heat exchanger design. Regardless of the heating application, startup and shutdown are sharp and clean and occur when the atomizing air is turned on and off by a solenoid valve. Transient smoke problems that have plagued the industry from its very inception are simply non-existent in the Airtronic burner. This can be attributed to the efficient atomization concept in combination with the dual atomizer design. The following experiments clearly illustrate how easy it is to light a finely atomized fuel spray. In the first sequence, a match is brought into the general vicinity of the spray. Notice how ignition takes place well before the flame encounters the boundary of the spray plume. In this next sequence, the sprays are ignited by a flint-type striker that is normally used with Bunsen burners or other small gas-fired equipment. The Airtronic burner was designed for the replacement market as well as for use with original equipment. As such, it will adapt to virtually any heating appliance sold in Europe or the United States. Installation is just a matter of removing the old burner and installing the new one. The installer must make sure the flame enters the firebox, but otherwise there are no special instructions to follow. For example, if the air tube protrudes an inch or so into the firebox, it will not adversely affect burner performance. The Airtronic burner will also tolerate contaminants in the fuel. The ingestion of modest amounts of air and water will shut down a high-pressure burner, but not so with the Airtronic. Here, the oil supply line is totally removed from the fuel, without the slightest change in the flame characteristics. As long as the fuel supply is re-established within a few minutes, there will be no shutdown and no combustion instability. The Airtronic burner was designed with very ambitious goals and to solve problems that have been with the industry for years and years. Although there are still problems to be solved, it is fair to say that these are minor by comparison to the technical strides that have been made with the introduction of the Airtronic burner. Appliances for boats and recreational vehicles use a number of energy sources to provide onboard convenience and comfort. Present-day appliances are powered by electricity, propane, kerosene, gasoline, alcohol, and ice. The diesel-fired appliance program is being conducted by a major appliance manufacturer and is based upon the premise that the owner of any boat or recreational vehicle would prefer to use a single fuel to operate all of his appliances. In this regard, diesel is the fuel of choice because it is safe, relatively inexpensive, easy to handle and store, and in many cases used in the engine of the boat or recreational vehicle. The new diesel-fired equipment being developed includes a refrigerator, space heater, hot water heater, and cooktop. All of these appliances have been designed for odor-free and sealed combustion. Since there never has been a diesel-fired refrigerator, the first technical challenge was to develop a burner so small that it would consume only 1 gallon of fuel every 2 weeks while operating continuously. After several basic experiments, a commercially available absorption-type refrigerator was fitted with a Babington burner containing an impactor. This glass prototype was sized to produce 400 BTUs per hour to match the heat output from the propane burner that normally powers the refrigerator. No other modifications were necessary. This new diesel-fired refrigerator has operated successfully for extended periods without signs of coking or carbon formation. The space heater for boats and recreational vehicles contains a miniature version of the Airtronic burner. It has a variable capacity from 5,000 to 15,000 BTUs per hour. This small burner fires directly into a heat exchanger, which is about 50% larger than a shoebox. The unique hot water heater is a cogeneration device because it generates electricity at the same time it produces hot water. The electrical power is produced by thermoelectrics and is sufficient to operate all of the onboard appliances simultaneously. This auxiliary source of power prevents battery drainage from the boat or recreational vehicle. In principle, thermoelectrics are simple. Electrical power is produced by maintaining a temperature differential across the thermoelectric modules. Normally, this is a very inefficient way to produce electricity because of the high heat rejection losses. However, when used in conjunction with a hot water system, the waste heat can be recovered in the useful production of hot water. Certain advantages of thermoelectrics are also appealing to the users of boats and recreational vehicles. For example, thermoelectric power is generated silently, reliably, and with no moving parts. In this prototype unit, the thermoelectric modules are totally encased in a cylindrical configuration. Heat on the order of 10,000 BTUs per hour is transferred uniformly to the hot side of the thermopile by means of a glowing mantle located in the center of the unit. Surrounding the outer shroud that covers the thermoelectrics is a cylindrical copper manifold with internal water channels. The rejection of waste heat and the subsequent production of hot water takes place as the water flows in and around the annulus area created by the outer thermoelectric shroud and the external copper manifold. This system generated more than 60 watts of power, which is more than sufficient to operate all of the diesel appliances simultaneously. At the same time, an ample supply of hot water was delivered at 140 degrees Fahrenheit. In the latest development effort, a burner with a maximum firing rate of 9,000 BTUs per hour was developed for a 2-station cooktop. This burner allows the main cooking surface to be regulated to any desired temperature between ambient and 1,000 degrees Fahrenheit. The secondary cooking surface is heated by the exhaust gases leaving the main cooking station. This makes its temperature cooler and dependent upon that of the primary heating surface. The temperature of the respective cooking stations is regulated by a single control knob that turns the burner on and off in a cyclic manner. Located directly over the vertical discharge of the burner, but under the glass ceramic cooking surface, is a perforated ceramic disc 3.5 inches in diameter. Under normal operation, this ceramic disc glows cherry red and radiates additional heat to the cooking surface. The diesel cooktop looks and performs very much like its electrical or gas counterparts. When the operator wants to cook, he simply turns on the control knob. After a few seconds, the ceramic disc begins to glow and the cooking procedure can begin. This concludes a summary of some new and innovative burners that utilize the Babington atomization principle. The Airtronic burner has enjoyed 3 years of success on the European market. The diesel appliance program is in its third year of development, with field testing scheduled to begin in 1988. The development of these small capacity burners, especially the refrigerator and the cooktop, provides convincing evidence that oil-fired burners can be developed for applications that once belonged exclusively to the gas industry and the power company.